Okay, let's begin. Okay, so let's start from the example. So I'm going to do this example together and we'll resume where we left. So let's look at this one. S be the surface of paraboloid on the upper part of the space and assume the orientation is upward. So upward doesn't mean that it's straight up. It means that if you have a orientation, if you have always two direction of orientation, you want to choose which one, the one that is towards up. Okay, so find the surface integral of the vector field 0, 0, z. So the vector field is always pointing up because the x and y components are 0. So let's try to draw the picture. So we have the surface given as the graph of two variable function. So it's upside down paraboloid. But we don't want the entire paraboloid because it's infinite. We only want the part that is on the positive side of that axis. So that's my S. And I also want the upward orientation. So I can choose that. So you can decide which one is inside or outside. But the notion of inside and outside is confusing because some people think that the outside is inside. So upward is better expression to indicate which direction we are looking at. So we are talking about orientation this way. Okay? So depending on the point that you're looking at, the orientation changes its direction. So you have to choose, you have to find the formula of your orientation. So let's think about the definition of a surface integral of a vector field. So by the way, the vector field is given specifically, but I'll write it the formula first and then plug that into the formula. So this is our notation, but the definition says if you want to compute the value assigned to this notation, you first need to take the inner product of the vector field with the orientation n, and then this is the scalar function, the real valued function. You need to take the surface integral of that scalar function. Now, think about the meaning or definition of the orientation. So it's a perpendicular direction to the surface. The way you can get that perpendicular direction is by the parameterization. Suppose that your parameterization is given by, well, let me write it in UV first, in UV parameters. So the easiest way of identifying a point in this surface is just set u and v equal to x and y. Okay, so I'm going to just set uv to be just x and y values of my parameterization, and z coordinate is given by 1 minus x squared minus y squared, but it's 1 minus u squared minus v squared. So with this parameterization, what I'm actually doing is I'm mapping my uv plane to x, y, z coordinate space. And since I identify uv as x, y, you can imagine this unit circle is the same unit circle that lies on xy plane. So in some sense, if you have a surface given as a graph of two variable function, you can always define a parameterization in this way. You always set the, so it's called a projection. So you can always identify a point on the surface with the point on xy plane when you project straight down to the xy plane. So let's use this one. there are other way of using other way of parameterization, but if I use this one, so the orientation is defined to be the unit vector perpendicular direction. Now the way to get the perpendicular direction is taking the cross product of two vectors parallel to the plane. So we are looking at the perpendicular direction to the surface, so we need to take the perpendicular direction to the tangent plane of the surface. So the tangent plane has two different directions parallel to, which is SU and SV. So SU means that when I move my point in U directions, it's the instant velocity of the point moving along the surface. So let's see, if I have point here, so corresponds to here, maybe here, then this is my movement in U direction. So when I move in this direction, then my corresponding point on the surface is moving toward this way. So that's my SU direction. And when I move this direction along the V, then I move in this direction in X, Y, Z coordinate. So my point on the surface is moving this direction. So that's my SV. So you have to choose the order of the cross product in order to get the right orientation. Since we want the orientation to be upward, which means the outward in some sense, we need to take SU cross SV. Because if I take cross SV cross SU, then you can see that from the right-hand rule that it goes inside of the surface, goes inside here. So this is the right order, SU times SV. Okay, so let's not plug in all the formulas here yet. So I'm going to just put this back in here. And this becomes S, F, inner product, SU, SV, SU, SV, ds. So the entire thing here is a function that I want to integrate over the first surface S. So now what's the definition of surface integral of a real valued function? Remember that you also need a parameterization. So we're going to use the same parameterization to compute the orientation. So here, this is my D and this is my S. So the definition of the surface integral is you integrate double integral. You compute the double integral of the function in terms of U and V. So here, the SU part is already in terms of SU and V. Now you have to write your original vector field F in terms of SUV by substituting XYZ with the parameterization. So here the vector field must be in terms of S and U and V. So plug in the parameterization SUV here so that you write X and Y and Z in terms of U and V. And then SU, SV, these are the same thing. Nothing to replace to SU, nothing to replace. But now, how do you change ds part here? So again, this is just notation. This ds is also just a notation. But when you want to compute the surface integral, you need to turn it into a double integral, which means that you need du dv notation here, right? Because you're integrating over UV plane. But you can't just change the ds into du dv because, as I said, you need a change. You need a change in the areas in the three-dimensional space to the two-dimensional space. So you need to multiply SU, SV terms. So this whole thing is the function that we want to integrate over. But this term is somehow the factor that you have to multiply in order to get the same area of the surface. So overall, disregard all the meaning of this, just look at the formula. We have canceling out between these two. So eventually what we get is integration over d of the vector field, substitute in terms of u and v, inner product with su and sv, du, dv. So you can follow the exact steps that I just did, but you can also plug in the parameterization directly into the final formula, because it's a simpler bit. We don't need to compute the size of the cross product anymore. So let's do from here. Okay, so the D is the circle. I'll just put it D here. And F is 0, 0, Z. And Z, I know that it's represented as 1 minus u squared minus v squared. And then now I need to find SU and SV. Let's see. SU is 1, 0 minus 2u. SV is 0, 1 minus 2v. So therefore, SU, SV is my 2u, 2v, 1. Okay. So I don't need to take the signs anymore, because I'm going to use this formula. So just directly put du, 2u, 2v, 1 here, and du, dv. So basically it's integration over d of 1 minus u squared minus v squared du, dv. Now from now you can use iterated integral to find its value, since it's simple double integration. If you want to keep the uv coordinate, then this can be written as minus 1 to 1 minus square root 1 minus u squared 1 minus u and 1 minus u squared minus v squared dv du, because you can look your domain D as bounded region of two graphs. So this one is v equals to square root of minus u squared, and this one is v equals to minus 1 minus u squared. So you have the bounded region, the region bounded by two graphs, upper and bottom, of the circular domain. And it's not hard. I mean, it's doable using this. But also you can use polar coordinate system by integration by substitution. So instead of using D, so I can use r theta coordinate. So if I want to cover entire unicircular disk, then I can change my r, the radius from the origin, from 0 to 1 and pi to 0 to 2 pi. So I can set this, say, v to be my new integrating domain, and the transformation t sends r theta to r cosine theta, r sine theta. That's my u and v. So I'm just reviewing all the stuff that we did in order to make sure that you understand everything. So picking up from here, if I want to integrate this by substitution, I'm integrating over v, which is in the r theta plane. So everything is in r dr d theta. But then what I need to do is change the function 1 minus in terms of uv into a function in terms of r theta. So u and v is r cosine r sine, so it becomes 1 minus r squared. And what do I need to multiply? I need to multiply Jacobian, because I'm changing uv to r theta. This is what I need to multiply, right? So you have to memorize that which Jacobian, which functions Jacobian should I multiply is done by just simple symbolic notation. I want to cancel out this dr d theta to make du dv right here. So that means I need to multiply Jacobian of this form, del uv over del r theta. That means I need to take the partial differential of uv, these ones, in terms of r theta. So let's compute. Actually, I think we've done this before, but I'll do it again. R theta is simply a 2 by 2 matrix, determinant of 2 by 2 matrix. First, you take the partial derivative of u, and then you take partial derivative of v. So this becomes determinant of cosine theta and minus r sine theta, and this is sine theta and r cosine theta. So this is just simply r. And when you plug into the formula, you need to take the absolute value, but r is always positive. Don't need to put the absolute value here. And now you can directly use the, you can change it to the iterated integral. So r is from 0 to 1, and theta is from 0 to 2 pi, 1 minus r squared times r. Now theta is 0 and 2 pi is the range for theta. 0 and 1 is the range for r. Be careful about the order here. So that now the final answer is 2 pi. Since there's no theta terms here, so you can consider everything inside of the integrand is the constant in terms of theta. So simply integration over r minus r cubed dr, and this becomes 1 over 2 minus 1 over 4, so therefore pi over 4. That's your surface integral. Okay? Any questions? Okay, so let's look at another example. So let's talk about the notation of surface integral. When you have a PQR vector field, it can be written as this form. So be careful about the order of the dx, y, and dz. So you have two d's every terms. And it means also you can rewrite this in terms of sum of these three surface integrals s q dz dx and s r dx dy. So what does each surface integral means? So this one is simply surface integral over the same surface of P00 ds. Okay, and this is surface integral of 0q0 ds. And this one is surface integral over 00r ds. So without going into deeper reason why we can do this, think about simply what we are trying to get from this surface integral. We have a vector field which is pointing directly to x-axis. There is no y and z-axis. Okay, so whenever you try to get the surface integral of a vector field, you're trying to get the flux. The meaning of the surface integral over a vector field is flux. It's the amount of water or fluid or current flowing through the surface over the time. Now, not over the time, it's per time. So when you have the current in the x-axis only, you only want to measure how much it's flown out in the perpendicular direction to x-axis. Because if you have a slightly slanted surface to x-axis, then you only want to measure how much it's been flown through directly across the surface. So you don't want to multiply entire surface of the slanted surface to the velocity of the current. So here's the idea about the picture of the picture here. So let's see. Here's our tube, and the water is flowing in a constant speed. And let's assume that this is my x-axis. Okay. So my vector field is v. Let me put it p here so that I get the same notation. So p, the water is flowing in the p velocity, whatever the unit is, meter per second, whatever. So the vector field is p00 because it's always always flowing in x-axis direction. Now I want to find out. So let's see. I have a surface that is covering entire tube inside. Okay? The surface could be a wiggly surface or the straight surface. It could be a slanted surface or a straight up surface, whatever. So I have a surface S. So F ds. It means it's the flux of the vector field. Vector field across the surface. So what is the flux? It's the amount of fluid flown across per time, across S per time. Okay. So I just want to measure how much water has been flown through the tube. Okay. So it doesn't matter whether I put the surface in this shape or that shape. So the shape of the surface only measures how much it's been flown through each point of the surface, but overall the flux, it only measures how much water has been flown through the tube. So maybe I should put it more detail. It's the amount of fluid flown in the tube per time, per unit of time, whatever. Now, what I need is, I only want to measure how much water has been flown directly across the surface that is perpendicular to the cube. Because that way I can measure the amount of flux easily. So instead of putting the surface in a wiggly way, maybe I can just put the surface directly perpendicular direction to the tube. So here, let's see here. Let's say this is my surface S. Okay. So then, what is the flux? I know that the water is flowing in this direction with the velocity p. So in that case, the flux is simply the area of S times the velocity p, right? That's the flux. So the p already has a velocity. That means it's the meter or unit of length per time, unit of time. So when I multiply the unit of length with the unit of the area, then it's the volume. So it's the flux is the volume per time that passed through the surface S. So if I had this surface straight up through the tube, then I get the exact flux easily by multiplying these two numbers. But the question is, what if I have a surface not straight up, like this one, wiggly? Then I need to take the surface integral. Okay. Assuming that if every point on the surface I have a certain measure of how much the water has been flowing and so on. But then what I need is not just multiplying the area of this wiggly surface on the top with the velocity v, because if I do that, then I can make my surface area arbitrarily large so that my flux could be arbitrarily large. So if I take a surface more wigglier than this one, like more going around and then going into the another side of the tube, then I can make the surface of this filter or whatever is has a arbitrarily large area. And that doesn't make sense. So how large the area of your filter is, the amount of water flowing through that tube must be the same. So that's why we need to multiply the orientation of the surface. So even if I have a surface slanted like this one, if I want to measure the velocity or flux of the vector field, and this is my orientation and this is my vector, I only want to measure how much it has been flown through perpendicular direction here. So I can take the projection of my vector field, and this becomes F inner product N. Oh, it's a bit dark here, so let me put it yellow here. So I can take a projection of a vector field to the direction of my orientation, and this is how much I want to measure that the water has been flown through the surface. So let's assume that this is just a small portion of the surface. Okay. Now, why should I just take this part? Because if I divide my vector field F into the sum of two vectors, one is the parallel direction to the orientation, and the other is orthogonal direction. Let's say this is F perp here. So let me put it more longer way here. So if I add these two vectors together, I get the entire vector field. So overall, I just want, it's true that I want to find out the flux of F, but when I take the decomposition of these vector field into two pieces, the part that it's pointing parallel to the surface has no flux. It doesn't go across the surface when I move in a parallel direction to the surface. So the flux of this vector field is 0. Okay? So I don't need to take the flux anymore. I only want to take the flux of this vector field. Okay? So this vector field and this vector field added to the original vector field. So flux of this vector field is same as flux of this vector field. So what is the flux of this vector field? It's simple, because it crosses directly perpendicular to the direction of the tangent direction of the surface. So I need to just multiply the area of this small portion of surface with the vector field or velocity of that vector field to get the flux. So that's what I'm doing here in a small area of the surface. I do it for every part of the surface to add all those fluxes to get the entire flux. So think about the case we have in here again. So if I pick the tube, direction of tube as x-axis, and let's see, this is my y-axis and this is my z-axis. I only want to know how much it's been flown through the surface perpendicular direction, but that's same thing as I put this surface projected on the YZ plane and then multiply on P. So here's the reason why. So we have, in some sense, I could draw in the three-dimensional, but easier to make it into two-dimensional picture. So let's say I have a projection on YZ plane. So I just depicted my YZ plane as a line here. So just meaning that it's straight up to the surface of this screen here. And think about when I multiply ds to, let's see, the the size of this vector field load. So let's see here. I want to have a flux, so it's a delta flux, small flux. It's same as F. It just means that it's the velocity. Sorry, so it's not really a good notation here. So let me put it this way. So let's put it this way. V here. It's the velocity of fluid. Okay. So I can get the flux by multiplying these two values, but I can do the same thing by taking this surface area, like this one. So if I have this zeta equal here, then then I can get this one. So this is the original velocity v of the fluid, but I only want to know how much it's been flowing through the perpendicular direction to the surface, which will come out shortly. So, so if this is the velocity v, I only want this velocity, not entire velocity, because I only want this part. So I need to multiply cosine. So I can think of this as a surface area times some portion of the velocity of the velocity of the fluid to multiply to get the flux. But I can do it in another direction, meaning that instead of thinking about this change of velocity, think about the change of area that we are trying to get, the flux. So I get the entire velocity of the fluid, but I only want to measure how much is flowing through the perpendicular or projected plane of the surface. So delta S times cosine theta. So this is delta S times cosine theta. So same thing, you get the same flux, right? So just changing the perspective from the change of velocity to change of area that we are trying to get the same value. So notation I introduced here as, let's see, P dy dz is, so it's over S. It's the, so P is the velocity, and dy dz is meaning that I only want to know how much the points on the surface moves across yz. I don't care about the movement in xz. So it's the projected surface from S. So it's projected onto yz plane. So this is the flux of P00 across S. Okay? So that's what I mean by this notation. And actually has a upshot. It's easy. It makes easier to compute in some circumstance. So whenever you saw this kind of notation, you remember that what we are doing here is not simply forgetting about the x-axis. We're just simply trying to project the surface onto the yz plane. So let's look at this example. I think we briefly went through this example last time, but I'll do it detail. So if you want to get this surface integral, there are two ways of doing this. One is just following the same definition of the surface integral, because this one, let's see, what's the vector field? The x-coordinate of the vector field is x, y-coordinate of vector field is y, and so this is p, q, and this is r. So it's x, y, z, ds. Okay, so this is your integration. So you can, in the problem, you have 6 different sides of the surface. So you can parameterize each side in parameterization. So you can add the surface integral of 6 different surfaces and then come up with an answer here. Or you can, so that's one way you can do it. Another way of doing this is simply look at this notation and then split them into 3 different surface integral. And each surface integral simply means that I want to see the surface change, the point changes in the point on the surface in these 2 axes. For example, in the first one, I only want to see the changes in xy plane. Look at other surfaces except for S2 and S4. All the surfaces has no changes in either one axis. For example, if you look at S1, it only changes across x and z axis. It doesn't change over y. So when you project this onto xy plane for this surface integral, you get a line, not an area. The area of a line is 0, so you don't have anything to compute, because what is the flux over the line? Since the line has area 0, flux is 0. So you don't need to compute over S1. Same for S6, S3, and S5. So only non-zero flux could be could happen over S2 and S4. So let's look at S2 first. On S2, now it's actually parallel to xy plane, so you don't need to parameterize anymore. It already parameterized in terms of x and y. But think about the points on the surface. As I said, when I notate the surface integral like this one, it doesn't mean that you forget the coordinate of z. You only want to change the changes in xy point, xy direction. But as you change the xy coordinate on this surface, z coordinate stays the same. So z coordinate is always 2. So here, the function z is constant over the surface S2. So what you're integrating on S2, so let me write this way. So here, so when you integrate over S2, you're integrating 2 dx dy. And now it really becomes simple double integral. So even though S2 is a surface on the 3-dimensional space, I only want to know how much it changes on x and y direction and multiply to the value 2. So I can just take out this 2 and S2 dx dy. So in some sense, this is the area of S2 projected onto xy plane. But S2 is already parallel to xy plane, so it is same as the area of S2. So area S2 is, it's a patch of 3 1x1 square, so it's 6. So how about S4? So I show you the picture again. S4 is on the plane, parallel plane where the z values are equal to 1. So instead of 2, you have 1. It's 1 times dx dy. So therefore, it's area of S1, which is 1. Okay. Now, let's do another one. Let's try this one. So it's easy to do this one. So let's try to get this one done. So look at the surface, which one has non-zero area when you project it on xz plane. So by the way, this is x-axis and this is z-axis. So when you project it on z-x-axis, S1 and S5 is the surface that has area. All the other surfaces are projected on the line, so no area. Now, I want to find out flux over the S1. Okay, that means this. Now, since I forgot to put this as a condition, but I mean the orientation of this surface to be the outward direction of the cube. So the orientation of S1 is towards a negative y-axis. Look at the y-axis here. So when the y-axis is moving up, this is the positive axis, positive direction. But the orientation of S1 must be the opposite of that. So it's a negative directions. So by the way, so when you want to find the area flux over the S1, the velocity that you need to multiply is y, and on this surface, all the values of y coordinates are 0, right? So all 0. So therefore, there's no velocity at all. So you don't have a flux. So let's look at S5. Now S5 has velocity. It means that the vector is flowing in direction in velocity of 1. That means it's flowing this direction in a positive y-axis direction. So this one. But however, what I want is the flux across the surface in the orientation direction. So orientation, this is my orientation of S5. So if the water is flowing in the same direction of orientation, you can say that it's flowing out. That means it's positive. But if it's going opposite direction, you can consider it's flowing in, right? So it's a negative of the flowing out amount. So when you want to compute the S5, so S5, it's -1, okay? Because the water is flowing in a velocity of 1, but the orientation is negative to that direction. So it's -1 of dx dz. So it's minus of the area of S5, which is -1, and so on. So you can do the rest of the surface integral. That makes sense. You have to think about the orientation whenever you try to get the integration done by this method. Even though it doesn't have it looks like doesn't have any sign assigned to it, but actually there's something more deeper into the mathematical side when you think about this notation. But we're not gonna go through that part. But anyway, so think about the orientation, even if you do compute the surface integral in this way. So you have to think about the meaning, think about the 3D picture of your orientation whenever you try to do this. So let me show you, let's do another examples. So this one is no 3D example anymore. So I'll show you more example. So let's see. So I have a vector field x, y, z, and 1. So I'm just making up the random vector field. Then S is, let's see, sphere of radius 1. Okay. I want to find out the vector flux, surface integral over S. And the orientation is outward. Okay. Outward from the ball of radius 1. So I want to find out this. So following definition has been done already, so let's try to do the other way. So I want to, let's see, translate it into the new notation here. So I want to write down the surface integral this way. So on xy, that's the direction of x-axis. I only want to know how much is flowing in yz plane. So it's y, z, and z is the y direction, so I only want to know how much is flowing zx direction. And 1 is the z-axis, so I only want to know dx dy. Okay? So that's my surface integral using in other notation. So let's first try to look at this one by one. So dx dy and dx dy. Okay? So how about the first one? So I'm looking at the surface as a projected plane on yz plane. But you're looking at the surface of the sphere. Sphere is not one-to-one identified with the projected point. Because if you project the sphere on yz plane, so it's actually symmetric whether you project it on yz or xy, it doesn't matter, it's always the circle. But when you project it, then the point on the projected surface, projected ball, is mapped to exactly 2 points, except for the boundary. So there are exactly 2 points on the sphere. So for example, if I draw that in here, so it's x, y, and z here. So this is my sphere here. So I am projecting on yz plane. So let me draw another. So it's hard to make a big circle visible here. So let me draw in this way. So there's a boundary of a big circle, not the big circle. Yeah, it's a boundary of a big circle on the yz plane when I project it on here. So there's a one side that is towards the blackboard in the positive x-axis, and one is the other side of this positive x direction. So there are 2 hemispheres, right? 1 and 2. So you need to separate those 2 because overall you want to run through entire surface, but if you just project it and then think about this as a one disk, then you forget the other side or the one side. You forget one of the side of the hemisphere. So you want to split your surface, the sphere, into 2 parts. S1, let's see. Let me distinguish in this way. So S, Y, Z plus to be the part where x is positive, okay? And S, Y, Z minus to be part where x is negative, okay? So let's split this first integral into sum of 2 integrals. So S, Y, Z plus xy dy dz plus S, Y, Z minus xy dy dz. And we'll do the rest of the part later. Let's first focus on these 2. Now, then you can identify your each hemisphere in one-to-one fashion to a disk in yz plane. So when I do that, let's say disk on yz plane is y squared z squared less than 1, and here x is equals to 0, since I projected on the yz plane. So this one is integration over dyz here, and let's put it xy here, xy, and dy dz plus, and here also dyz xy dy dz here. But now the thing that you have to memorize is that we're not actually looking at the projected plane. We're actually looking at the point on the hemisphere. We simply want to move my point on the disk in YZ plane to identify the point on the surface. So x here in two different surface integrals are different x's. So this x is the x coordinate in s, y, z plus, and this one is x coordinate in s, y, z minus. So you see what I'm saying? So the first surface integral, I want to change my point on this hemisphere. So therefore, my x coordinate is following these conditions that x has to be bigger than or equal to 0. And here, I'm looking at the point on the other side of hemisphere, so my x must be following this condition. So on the positive x hemisphere, this x must be square root of minus 1 minus y squared minus y z squared. And how about here? Here is minus 1 minus y squared z squared. So we have more, by the way, but let's focus on this part. So the domain is just the same, the disk, the d, y, z, but in here we have y 1 minus y squared minus z squared dy dz, and then here we have minus y 1 minus y squared minus z squared dy dz, d dy. Okay. Well, actually now you can carry out the computation separately, but without doing that, you know that this cancels out because now it's everything's the same. So on the first sum end, you have an integration over yz over the region in yz plane of this function, and you have exactly the same function with the different sign on the exactly same domain, so you can get the same canceling out here. So these two are now same but different sign, so it cancels to 0. Okay. So let's do the second part here. Well, you'll get the same thing. You get the negative and the positive again. So, but you can imagine that this same thing happens, that when you try to get the integration over the surface on these vector fields, so then you want to just simply know how much it changes over xz direction. So you're projecting your surface on xz plane. So you're integrating over the plus hemisphere zx according to zx. Forget. So just abbreviate the notation here. So minus zx. And what's the next? So the last one is xy. And there's a 1 hiding here. So his s xy plus and s xy minus. So without writing all the details, so think about here and here. So on this side, I want to know that I'm looking at my y coordinate to be positive value. So x is x and z is z, but y is plus square root of 1 minus x squared minus z squared. And here I'm looking at y as a negative value, so it's 1 minus square root of 1 minus x squared z squared. So whenever you have a y coordinate, y variable inside your one of these two surface integral, then you have to plug in these formulas instead of just plus or minus, the same. So by the way, we actually don't have it. So don't have the y here. We don't have y. We only have z here. So let's see. We are integrating over the disk on z x-axis, z dz dx, and integrating the same thing, z dx dx. And how about here? Okay, so that's actually simpler. So these two are the first two integrals, and the last two integrals are having no, it has a constant function, 1, so nothing to substitute. We only are taking the integration over the one hemisphere and the other hemisphere. So what does that mean? Well, it simply means that we just take the dxy and dx dy, and same thing for dxy and dx dy. Okay. So it's different from the surface integral of that hemisphere, since we are looking at the projected surface here. So because of the notation here, we're not taking the area of a hemisphere, we're taking the area of a projected surface. Okay? So that's going to be the area of a disk. So let's try, actually this one becomes 0 because that is, you will see that this actually becomes 0 because it's minus 1 to 1 of minus 1 minus z square and 1 minus z square dx dz here, and the same thing, so it's twice of this, and then this part, it's also twice, but we are taking integration, double integration over xy plane on the disk, the unit disk, so we know that what that is, so it's a pi, so it's 2 times the pi, 2 pi, and this whole thing becomes 0 because if you imagine what will become is that, but that is an odd function, so if you integrate over minus 1 to 1, it's always 0. So it's 2 pi. Okay. So you're not going to see this one in the other traditional text because this is somewhat, in some sense it's advanced, but I think it more has a meaning, it has more meaning than knowing the actual definition of the surface integral. This notation also generalized to mathematical concept called the form, differential form, and we'll talk about how to use this kind of notation in understanding of the Stokes theorem later. Okay, so I'll give you a chance to exercise more if we have time after we've gone through it at the end of this lecture. So let's move on to another part of the story. So here's some more notion of the domain. So let me define some characteristic of domain. So sometimes we want to impose some condition on the domain. One is the connectedness, and the other is simply connectedness. So it's the connectedness is it's intuitively what it means. So it's connected, meaning that any 2 points in that domain are connected by a path. So it's connected. However, when we say the domain is simply connected, it doesn't mean that it's about the path. It's about whether it has a hole or not. So simply connected means that it has no hole, okay, no hole. But actually, it has a little bit, complicated when the dimension of the region is bigger than 2. So the rigorous definition of simply connectedness is that if you take any simple closed curve loop, it means a loop, then you can continuously shrink that loop into a point. So for example, if you have a disk, then if you take any loop that surrounds a point, then you can shrink your loop into that point continuously. But if you think about the, some annulus here, so the inside of the circle is empty, and you take the loop around that hole, then you cannot shrink that loop into a point without jumping over some point, right? So you are kind of blocked here. So if you want to shrink your loop, you have to jump. Means that you need a discontinuity in the process. So this one is not simply connected. This is simply connected, okay? So that will come up later when we talk about the potential function. So let's talk about orientation. So I think I briefly explained this before. So whenever you have a connected region, connected domain, then and you have a boundary of that connected domain, you have a notion of positive orientation. So what is the positive orientation? It's the direction when you walk along that orientation that your region is on your left side. So it's not always counterclockwise or clockwise. It depends on where your region is. So think about this annulus. So on the outer boundary, the counterclockwise is the positive orientation, and in the inner boundary, it's the clockwise, which is the positive orientation. So what's the Green theorem? Now, since the reason why we talk about disconnectedness and then positive orientation is to explain this Green theorem. Let's say our domain D is connected domain. It's two-dimensional domain, by the way, two-dimensional connected domain with a piecewise smooth boundary curve. So it has a boundary. And we assume that this boundary is positively oriented. So we know the notion of positive orientation. The reason is that we want to know how to compute the line integral. So Green's theorem says if you take the line integral in a positive orientation, then it can be done exactly same by the double integral, or the value that you compute as a line integral is same as the value you compute as the double integral. So it's quite weird, but it's very useful. We'll skip the proof here. Let me show you an example. So let's find an integral of along the curve in a positive oriented way, like this one. Now, let's do it the line integral directly, and then let's use the Green theorem and check whether these two are the same. So line integral, well, it already split it into two parts. So as you can see, I can take, so here, line integral as C1 plus C2, C3, C4. So when I go along the C1 first, C1 is this one. I don't have changes in y direction. So dy becomes 0. So I have y squared dx. That's all I need to compute. And along the C2, I have dx equals to 0, so dy, and C3 and C4, dy, okay? So what's the integration over C1? So I only need to know where my x changes. It changes from 0 to 1. Okay? And what is my y? Well, y is always 0. So no matter what the value is, it's always 0. And about C2, I'm moving along this direction. And x is 1, and y is changing from 0 to 1. So it's dy from 0 to 1. And on C3, now I'm moving backward from 1 to 0. And y is 1. And how about the C4? Now C4 has value x equals to 0 all the time. So it's going to be 0 anyway. So the integration that survive is this one and this one. So it's the same integration, only differ by the orientation. So it's going to be 0 anyway. So let's try to get the green theorem applied here. So it says, the green theorem says, so this is your p and this is your q. So p is y squared and q is x squared. It's same as double integration over qx minus py dx dy. So it's 2x minus 2y dx dy. So domain is rectangular domain, so I can make it into an iterated integral from 0 to 1, 0 to 1. So let's try x first. So it's x squared minus 2xy from 0, 1 dy. So it's 1 minus 2y dy. And y minus y squared, it's 0. So you got the both 0. Okay? You got the same value. 0 is not important. The important thing is that you get the same value from the line integral and the double integral. Okay, so let me skip the proof part. Okay, so here's the way you can apply the green theorem. So why do we need the green theorem? Basically, you want to interchange the line integral to double integral or the double integral in the line integral. But usually, the situation where you need the green theorem is when you have a complicated line integral and you want to compute this using the double integral. So in that case, let's say I have this kind of mirror image of C-shaped domain. If I want to find out the line integral over the boundary of this entire domain, then I can split, and using the green theorem, I need to think about way to split this. Because if I take this entire line integral, okay, so I can turn it into the double integral over the entire domain, then I need a way to compute this double integral. So the easiest way of taking the double integral is iterated integral. So then you need to know the order of your iterated integral. So for example, if I want this iterated integral in dx dy order, then I need to define my domain in terms of d equals to, let's say, c is from y is from c to d, and x is from g1 y to g2y, right? So in that case, I can write my iterated integral like this one, g1y, g2y of some function here, so in terms of x and y. But then the problem is I cannot get a single g1 and g2 for this type of shape, this shape region. I need to subdivide it into smaller pieces so that I get the representation of the region in this way. So for example, let's look at this one. So if I want this type of representation of domain, I need to split my domain in this way, horizontally here. Because now I can see that each region is changing the y coordinate in one point to another, and the bound of my x value, the lower bound and the upper bound, is now governed by a curve which given as the graph of a function. So for example, this one, D3, look at these three here. So imagine that vertical axis is y-axis. Y is changing from here to here, right? Every point on D3 is y-axis are from here to here. And the lower bound, the minimum value of x at each y level is bound by this curve and this curve. So you have a single curve, single type of curve. And this curve can be represented as a graph of x equals to some function of y. And same for D4, and here is a small one, D6 and D5. So here, D5 is somehow, you need to separate into two pieces, one from here to here, and then one from another here. Okay? And if you don't want to use this representation, maybe you can, so in some sense, it's the I that you can write your iterated integral. If you don't want this, then let me be consistent with the notation above here. So I is actually the upper script in this case. So if you don't want this, maybe if you want to integrate dy dx order. So x first, that means we want to make x from a to b, and y is from, let's say, g1x to g2x. Okay, then x is from a to b, y from g1x, g2x of some value here. Then you need to subdivide your region in the vertical direction. So in this case, look at this one, D4. Your x is changing in a constant manner from here to here, but y has two bounds, a lower bound and upper bound, depending on where you're looking at. So these curves are governed by a graph of a function, and same for others. So this one is more convenient than this one, of course. So you have to choose which one is convenient to compute the integral. I think this one is actually getting complicated because you have a corner here. So, but in this picture, you can separate each region, the separate partitioned region, into a single function. The bound of y values are governed by a single function here. Right? So let's look at this one. I want to find the surface line integral along the curve, which is, sorry, so I didn't mention that this is the boundary of the positively oriented. Okay? So let's say C is the boundary of the region bounded by two graphs of functions, y equals to x squared and x equals to y squared. So you can imagine that this looks like this one. So y equals to x squared, x equals to y squared. This is your D. And C is the curve, positive oriented, so this is the orientation of your curve. I want to integrate this complicated two-dimensional vector field. So now you have to use the Green theorem. So instead of just try to parameterize your curve and use the same definition of line integral, which is possible numerically, but you don't need to. Now let's try, so this is your D. Use the Green theorem. First of all, you have to check whether the conditions of Green theorems are met. So what's the condition? The underlying condition is that every function we're dealing with is the differentiable function. So you have to first check whether all the functions, the component functions are differentiable functions. These are components, and these are consist of the polynomial or exponential sine, cosine function. That's fine. And also, you have to think about whether these functions are well defined, which means that differentiable inside the region. So this region, the bounded by two graphs. Of course, because these functions are differentiable on entire plane, so every conditions are met. So we can use the Green theorem. So let's turn that into a double integral. This is your Q and this is your P. So Green theorem says it's Qx minus Py dx dy. And then what is Qx? It's 2. So it's 2. And what is Py? It's 2y, right? So it's getting really simple. And dx dy. Now it's up to your choice whether you represent your d in xy direction, xy order, or yx order. So let's say I want to see in this way. So x is changing from 0 to 1, and y is from x squared to square root of x. Then I have to write my double integral into an iterated integral this way, dy dx. Okay. So then rest of the calculation is easy. So this one is actually done the other way without any splitting. So y is from 0 to 1 and x is from y squared to square root of y. But as I said, if your domain is not, the representation of your domain is not interchangeable, then you have to split the domain into pieces so that you can write in the other way. So this one you can use any one of these representations. Okay. So we'll actually look up this identity more detail when we talk about the Stokes theorem, but let me briefly mention what this means. So let's look at this first equations. So this is simply the Green theorem. So remember, so I think you have to remember this one. So there are a few things that I require students to remember. This is one of these few things. So just remember this formula as the standard form of the Green theorem. You have a Q and you have a P. So in some sense, you interchange the x and y. So instead of px, you get the qx and py, and you take the subtraction. So that's a Green theorem. But then you have to apply, if you assume that you apply the same Green theorem to this type of line integral. So these serve as the same q, but now the p is changed to minus p. So therefore, when you plug into your, so it's not pq. Sorry, it's qp here. So what I tried to, it's not that the identity is wrong, but what I tried to meant is I want to have px plus qi. Okay, so here, instead of q, so here, if you have vector field not pq but minus q comma p, then the line integral of that vector field becomes the double integration of px qi, which is the divergence, right? So when you put the Green theorem applied to this type of two different line integral, you end up getting the double integral of these scalar functions. One is qx minus py, the other is px plus qy. So what does that mean? Well, it has a meaning. Well, first of all, when you take the line integration of the original vector field, then you are trying to compute the work done by the vector field along that curve. So so again, this curve is a closed curve, right? It comes back to the original position. So It's work when you try to go one loop around the point in a circle in some sense. So it doesn't have to be circle, but anyway, if you make a small circle around the point, then you have to do some work, and that's the work done by the vector field. And it says, the Green theorem says that this work done is same thing as integrating some function, qx minus py, whatever that is, over that region. So in some sense, if you want to make one object circle around one point, it's same work as if you're rotating that object. So think about propeller. So you want to rotate a propeller. So maybe it's the wind that's trying to rotate the propeller, maybe the propeller of a wind turbine. So then you want to have a work done. You want to calculate how much the work has been done to that rotation. So you can compute this, instead of line integral, you can compute the amount of this rotated region, the amount of this term integrated over the area of that rotation to get the same value. So in that sense, this term is called the curl of vector PQ. Okay, so the curl somehow means it's a rotation, right? So how about this one? Okay, so if my vector field is PQ, and what is minus QP? So PQ is PQ is pointing this direction, minus QP is always perpendicular to that direction. Because if you take the inner product, it's 0, right? So always perpendicular. Okay, so what is the meaning of integrating minus PQ? So as I said, integrating PQ over the curve is how much you have been, how much the vector field has done work along the curve. So this is the work done on along the curve. You only measure the tangential work, tangential velocity along the curve. But here, what you're trying to get for the integration of minus QP is how much it has flown out through the curve, because every time you're trying to get the integration in the perpendicular direction to the tangential direction. So what does that mean? So it's a flux. So on the second line integral, you're actually computing the flux. So you don't confuse with the flux of the surface integral. It's the same idea. Because in the surface integral, you're just trying to get the three-dimensional picture, meaning that the fluid, whatever, is flowing through the surface in the three-dimensional space. In here, imagine that your current or water or air is very thin layer on the plane, and you want to know how much the water or air has been flown from one domain across the boundary of this curve. So that's the flux, two-dimensional flux. And look at the right-hand side. It says your flux is same as integrating this PQ plus QI, PX plus QI over that region. Well, when do you think there is a flux across this closed curve? So think about the current. Think about the closed curve and think about the current of water flowing through this closed curve. So some part of the curve, the water is flowing in, and some part is going out. So water is incompressible substance. So if some water is coming in amount, some amount, then the same amount has flown out in the closed curve. So you don't have a flux because nothing is actually making inside of there's no amount that actually made access to the amount that is flowing in. But think about you're boiling something, like boiling on air, so that the air inflates, the volume increases inside of the region bounded by the curve. Then there is a volume of air that is flowing out from this across this curve. So that's the flux. That's the flux. And here on the right-hand side, the Px plus Qy, the divergence, is somehow measuring how much of the air, whatever the substance, is inflating inside of the region bounded by the curve. So that's why it's called the divergence here. So the Green theorem is simply a two-dimensional version of the meaning of the curl and divergence. So we defined the curl and divergence in three-dimensional vector field, but this is the two-dimensional version of the meaning of it. But we'll discuss more detail when we talk about the Stokes theorem. But here, just think about why has to be done, not why, but just the meaning of these two, curl and divergence. Okay, so here's the another application of the Green theorem. So Green theorem not only gives the meaning of the curl and divergence, it also gives the way to compute the area inside the region bounded by some curve. So this area that you can see on the right is the area bounded by this parametric curve. I want to find its area, the actual area. So how do you find the area? Well, let's think about this way. So if I had x and minus y and take the line integral like this one, so y dx, y dx plus x dy, then the Green theorem says that it's same as, so this is my q and this is my p, right? Qx minus py, so it's 1 minus 1 dx dy. So it's actually 2 of the area d, right? So the area of d is 1/2 of the line integral dx x dy. So you're actually using the line integral to find something. So instead of using double integral, you can use line integral to find the area. So let's try to compute this. So we already have a parameterization. So this is 1/2 of 0 to pi of y, which is sine cube, times dx. What is dx? So x is this one. So you have 3, the derivative of this is 3 times cosine squared t minus sine t dt. And what is x dy? So x is cosine cube t, and dy is derivative of sine cube 3 sine squared t cosine t dt. Okay, so let's see. There's a common term. Oh, I forgot the minus one. So minus one here. So it's a plus plus. So let's see here. how many sine? Sine is 4 and cosine is 2. And here cosine is 4 and sine is 2. So you get the sine square, cosine square times 3 from 0 to 2 pi, 1 over 2 dt. So that's your integration. And this whole thing becomes square of sine and cosine. And I can make this into half of sine 2t. So this becomes 3 over 8, 0 to 2 pi, sine square 2t dt. So this is 3 over 8 times 2 pi, which is 3 pi over 4. So the area of this region is 3 pi over 4. Okay, so what's the point of getting the area of this weird shape? So actually there is a nice application to this. So think about the polygonal region. So we have n points as a vertex of a polygon. I want to find out the area of this polygon. All the information I know is just the location of my vertex. How do I get this? You can actually take the area, exact area, by taking lots of determinants, like this one. So how does it come from? So think about the curve as a boundary of a polygon, counterclockwise orientation. So I want to take the line integral of this, because that will give me the area enclosed by this curve. But then, what is my curve? The curve is the boundary of a polygon, so it starts from x1, y1 to x2, y2, and all the way back to xn, yn. So let me label this line C1, C2, and Cn here. So I'm going this direction. So let's think about C1 first. The line integral on C1 of these vector field is that I can parameterize C1 into the following. C1t is x1, y1 plus t x2 minus x1, y2 minus y1. So in that way, if I have t equals to 0, then I am at the x1, y1. When t equals to 1, then I have x2, y2. So I'm going straight from x1, y1 to x2, y2. So this is my parameterization. And x and y are x1 plus x2 minus x1t, and y1 plus y2 minus y1t. So if I plug that in to my line integration, so y is this one, minus y actually, y2 plus y2, y1, sorry. So y1 plus y2 minus y1t times, what is t? Dx. So it's a derivative of this x in terms of t. So I have x2 minus x1, and then x is x1 plus x2 minus x1t times dy, which is y2 minus y1 dt. Okay, so there are lots of cancellation. First of all, let's see. Look at this one. This one and this one have the same factor. It's x2, y2 minus y1 times x2 minus x1 times t. So these all things cancels out. So what left is 1 over 2 of minus y1 x2 minus x1 plus x1 y2 minus y1 dt. Okay, so it's the constant. So and you can see that there is also another cancellation with this one and this one. So what is left with is 1 over 2 of C1. Now you don't have to keep the C1 here because t is the parameter, changes from 0 to 1, is x1 y2 minus x2 y1 dt. So that thing, the inside of this integral, is exactly the determinant of x1, y1, x2, y2. So that's the line integration of the first line segment of the boundary of a polygon, C1. So you do the same for C2 and up to Cn, but be careful when you take the Cn, you're taking xn, yn to x1, y1. So when we take the notation like this, i's range from 1 to n, but when I is n, you're taking xn plus 1, yn plus 1, which doesn't exist, but we consider in the notation this xn plus 1, yn plus 1 is actually equals to x1 and y1. In that case, you can make the boundary come back to the original point, x1 and y1. So how do you make this as an application? So let's say you have a random curve. Okay, so you want to find a random the area of that random curve. So the curve is closed curve, let's say, and you want to find the area of the region bounded by this randomly drawn curve. So you can approximate these curves as a polygon of lots of vertices. Okay, so that's always the case. When you have a curve, you have to approximate it into a polygon with lots of vertices. And then you can use this formula to find the area of that polygon. So I showed you the gimmick of the game before, but it's a simpler game. I'll put the code on the Notion site with the Colab. So this one simply asks you to plot or click the vertex point, and if you click the given number of vertex point onto the screen, then it gives you a picture of your polygon and then computes the area of the polygon. So you have the task of the 8th project is to make it into a fun game incorporating some mathematical theory inside. So, well, the direct mathematical theory behind is how to find the area of the polygon. So assume that we have certain x and y coordinate and scale behind this screen, and you just want to find out what's the coordinate of these points that the user clicked on, and then you just simply use the formula I explained. But here's the important thing when you do this. So when you draw the polygon in this nice way, counterclockwise, you get a positive value as an area. What if you go backward, like clockwise direction? You get a negative value, right? You get a negative value because you change the orientation of the line integral. So, okay, so maybe it might be a good way to do more on this project from this prototype. Try to get the area regardless of the order of the vertex that user input, and also regardless of the convexity of the points that your user put it into. So for example, if the user put the points right inside of this polygon, then you don't want to have a polygon in a weird sense, like going into and going out. So you just want the polygon that is surrounded by the outermost vertex of the polygon, right? So in some sense, you have to find out the algorithm to determine which points are the outer points and which points are the inner points, and then just compute the polygon computed by the outermost vertices, And then you have to order them in a counterclockwise manner so that you get always a positive value for the area. That might be a task that you can put, but it's not mandatory anyway. So that's a very simple game. So there's nothing hard about it. It's actually simpler than the Crofton formula, Crofton formula game. So I've been just explaining all the time throughout this lecture, but is there any questions about the stuff we discussed so far? We can have a brief discussion about any question if you have. Who's doing this project? Raise your hand if you're doing this project. Oh, you're doing this. Okay, right. Okay, so. So idea is you have to make your game a bit more fun than this one. So it's just there's no element of competing or challenging. So try to think about how you can incorporate the line integral concept into this kind of game. So using the Green theorem. So for example, you can mix up the Cauchy-Crofton formula into this game, or you can also mix up the concept of line integral. Well, let's say you can think about, well, just be creative. I have a lot of thought, but let's say think about how you could make a line integral element added in this game. So here it simply looks like it's just finding the area, but you can make the user to or get the line integral as close as possible to this some kind of value by assigning a point, assigning a curve onto the screen on top of this area finding feature and so on. So this is always just the two-dimensional part, so I don't think it's going to be hard at all. You can also make it into a three-dimensional picture. Well, in that case, you need something that about surface integral and also the 3D projection onto it. But just be creative. Just make it more how do I say? So if you are doing this project, I think this is a lot important than the first project, because once you made this kind of program, then you can make it visible to others by publishing your work to any website. There are lots of free websites you can publish your this kind of application done by the Python code. So then once you upload it in there, it's there forever. So you can always put a link to your CV or resume so that everyone can see what you have done in your on your class or in the school years. So I think it's very important that you left your work done in some space that everyone can see publicly. So this one is very important. I think this one might be a way you can actually publish your work visibly. So, all right. So next week, I think I will try to finish the lecture by next week. So So how many weeks do we left here? So we have 2 weeks before the final. So if I finish the lecture by next week, I can give you 1 more week for preparation of your project. So we're gonna have a presentation on the final weekdays, but I want to make sure that everyone is doing the project properly, because not many people are coming these days. I'm not sure whether they're doing. I'm not even sure whether everyone has their group. So I want to make sure that everyone is doing their work. So that's my plan. So next week we're going to talk about the Stokes theorem and also the last project. And it's also about the game, but I haven't made the prototype of the last project. So if you have any idea about last project, then share me an idea, that might be great. So if you have any question, let me know. Otherwise, let's see you on Wednesday, next week, Wednesday.